Deep on this one.
You came prepared.
Definitely. I've got quite a few research papers here actually. It seems like this Sigmoid attention is really getting some attention.
Well, it's a fascinating topic, right? It's like taking this core component of transformers, the attention mechanism, and flipping the script a bit.
Yeah, instead of the usual softmax, we're looking at Sigmoid. Could it be better? More efficient? Who knows? That's what we're here to find out.
Exactly. So we've got the theoretical stuff, the mathematical underpinnings of how sigmoid attention works. Then we've got some papers that actually put it to the test, comparing it to softmax in terms of computational efficiency. And then we've got some real-world benchmarks too, language modeling, image classification, even speech recognition.
It's all here. So, where should we begin?
Well, I guess the first step is understanding, how sigmoid attention actually differs from softmax. What's the fundamental difference?
Right. At the heart of it, attention mechanisms are all about figuring out which parts of the input data the model should focus on.
It's like a spotlight, right? Shining it on the most relevant information.
Exactly. Now, with softmax, it creates a probability distribution, so the brightness of the spotlight on each piece of data is relative to all the others.
Okay, so everything's kind of balanced out.
Right. But with Sigmoid, it's different. It uses an element-wise Sigmoid function, so each piece of data is treated independently.
So it's not about relative importance anymore. It's about the absolute importance of each individual element.
That's a good way to put it, yeah. It's a pretty fundamental shift.
So does it even work? Can a transformer actually learn effectively with this independent scoring system?
Well, that's the amazing thing. One of the papers we have here actually proves that transformers with sigmoid attention can still be universal function approximators.
Whoa, hold on. So even with this totally different way of scoring relevance, they can theoretically still learn any mapping between input and output.
That's right, given enough data and computing power, of course. It's pretty mind-blowing when you think about it.
Yeah, that's pretty amazing. So if sigmoid attention is theoretically just as powerful as softmax, why aren't we seeing it everywhere? There's got to be a catch, right?
Well, there are always trade-offs. One of the challenges with sigmoid attention is something called large initial attention norms.
Okay, now we're getting into the technical stuff.
It's a bit complex, but basically during training, sigmoid can sometimes lead to instability. The model can jump around erratically instead of learning in a smooth and steady way.
So it's like it has all this raw power, but it needs some careful handling to really harness it effectively.
Exactly, and that's what a lot of these papers are exploring, different techniques for stabilizing sigmoid attention during training.
So what are some of these techniques? How are they taming this wild beast?
Well, one approach is called alibi, short for attention with linear biases.
Alibi. That's a catchy name.
It's a clever idea. It introduces a positional bias to the attention mechanism.
So like giving the model a little hint about where to focus its attention.
Exactly. And it turns out this positional bias can be really helpful. It's kind of like how humans naturally pay more attention to the beginning and end of a sentence.
Makes sense. So by adding this bias, they can nudge the model's attention to a more stable starting point.
That's the idea. Another technique they're using is called layer scale.
Layer scale. And what does that do?
It basically adjusts the scale of the attention output.
So it's like a volume knob fine-tuning the intensity of the attention signal.
Yeah, you could think of it that way. It prevents those wild swings in the attention values during training.
Okay, so it's all about control, keeping that raw power of sigmoid in check.
Absolutely. And then there's another technique called hybrid norm.
Hybrid norm. All right, you're gonna have to break this one down for me.
This one's a bit more involved. It's a modified normalization technique that combines pre-normalization with normalization of the attention output.
Double the normalization, double the fun.
Something like that. It's essentially a double-check system to ensure the data stays within a stable range throughout the learning process.
Okay, so like adding some shock absorbers to the model's training regime makes sense. But let's be honest, even with all these fancy techniques, what good is a powerful AI model if it takes forever to actually do anything?
Yeah, you're absolutely right. Efficiency is key, especially as we're dealing with increasingly massive models and data sets.
Exactly. So is sigmoid attention doomed to be slow and clunky?
Not necessarily. That's where this implementation called FLASHSIGMOID comes in.
FLASHSIGMOID. Okay, now that sounds interesting. Tell me more.
It's specifically designed for memory efficiency and speed, especially for handling those extra long sequences of data that are becoming more and more common.
Okay, so they're thinking ahead.
Definitely, FLASHSIGMOID leverages techniques like tiling and kernel fusion.
Tiling and kernel fusion. I'm all ears.
Tiling is all about breaking the data down into smaller chunks so it can be processed more efficiently. In kernel fusion combines multiple calculations into a single step to reduce overhead.
So they're streamlining the whole process, making it lean and mean.
Exactly. And the results are pretty impressive. They actually benchmarked FLASHSIGMOID against Flash Attention.
Flash Attention 2. Now that's a name I recognize. That's like the gold standard for efficient softmax attention, right?
Exactly. And yet this FLASHSIGMOID actually outperformed it in terms of inference kernel speed on specific hardware.
Wait a minute, are you saying Sigmoid beat the efficiency champ? That's a serious contender,
It definitely is, but of course, computational efficiency is just one piece of the puzzle.
right? We need to see how it performs in the real world.
Absolutely. That's the true test. Can sigmoid attention actually deliver on its promises in real-world tasks? That's what we'll dive into next.
Okay, I'm ready for it. Let's see what this Sigmoid attention can really do. So we left off with Sigmoid attention beating the speed champ. But that's just one benchmark, right? The real question is, can it handle the complexities of real-world tasks? What about language modeling, for example?
Ah, yes, language modeling, the domain where transformers first made their mark. Well, the researchers really dug deep here. They trained large language models using both sigmoid and softmax attention. And the results, particularly at shorter context lengths, were pretty surprising.
Surprising in a good way or the bad way? Did Sigmoid live up to the hype?
In a good way. For shorter chunks of text, sigmoid attention actually matched the performance of softmax.
So it can capture the nuances of language, generate coherent text, just like its more established counterpart.
Exactly. It's like it's able to understand and process language just as effectively as softmax, at least for shorter sequences.
Interesting. So for tasks that don't involve processing huge volumes of text, Sigmoid is a viable option.
The data seems to suggest that, but things got a bit more interesting when they pushed the models to handle longer context lengths.
Ah, so that's where the cracks start to show.
Not necessarily, it's just that at those longer lengths, sigmoid attention needed a little help from those stabilization techniques we talked about earlier, like hybrid norm.
Right, to keep those attention norms in check.
Exactly. It's like those longer sequences really tested sigmoid's limits, and those stabilization techniques proved to be essential for maintaining performance.
Makes sense. So it's not a clear-cut victory for Sigmoid in the language modeling arena, but it's definitely a strong contender, especially for shorter sequences.
That's a fair assessment, but let's move beyond the world of words and into the realm of images. How does sigmoid attention handle visual data?
Now that's a whole other ballgame, right? Images are so different from text.
They are, but transformers have shown to be remarkably adaptable. They've been successfully applied to image tasks using a specialized architecture called vision transformers.
Right, vision transformers, I've heard of those.
Well, the researchers used vision transformers with both sigmoid and softmax attention for supervised image classification.
Supervised image classification, so basically teaching the AI to recognize different objects in images.
Exactly, like distinguishing between a cat and a dog or a car and a bicycle.
And how does Sigmoid fare in this visual domain?
Impressively, actually, it matched softmax attention's performance in both training and evaluation.
Wow, so Sigmoid can handle pixels and patterns just as well as it handles words and sentences? That's pretty remarkable.
It seems that way. It's really making us rethink the possibilities of attention mechanisms. It's not just about language anymore, it's a much broader concept.
Absolutely. So we've seen Sigmoid hold its own in language modeling and image classification. But what about speech recognition? Can it keep up with softmax in the auditory domain?
Speech recognition is another crucial area for AI, right? It's the foundation of virtual assistants, automatic transcription, and so much more.
Exactly. So did they put Sigmoid to the test in this domain?
They did, and with the right bias initialization, sigmoid attention actually performed similarly to softmax attention in speech recognition tasks.
Similar performance, so no significant drop in accuracy.
None whatsoever. And importantly, it maintained its stability during training.
So it seems like Sigmoid is proving to be a viable alternative to softmax across multiple domains, language, vision, and now speech.
The evidence is definitely pointing in that direction. But the researchers didn't stop there. They also wanted to understand how sigmoid attention behaves under more controlled conditions.
Controlled conditions, what do you mean?
They conducted experiments with simpler synthetic tasks to isolate specific aspects of the attention mechanism.
So it's like running experiments in a lab setting to really understand the nuts and bolts of how sigmoid attention works.
Exactly. One particularly interesting experiment focused on sequence length generalization.
Sequence length generalization. Now that sounds important. What is that exactly?
It's all about testing the model's ability to handle sequences of data that are longer than what it was trained on.
Right, because in the real world, you can't always guarantee that the input data will perfectly match the training data.
Exactly. And what they found is that in some cases, sigmoid attention actually demonstrated better generalization capabilities than softmax attention.
Wait a minute. Better generalization. Are you saying that sigmoid might actually have an advantage when it comes to handling unexpected longer sequences?
It's a possibility that warrants further investigation, but it's certainly an intriguing finding. It suggests that Sigmoid's unique approach might lend itself well to adapting to new and unseen data.
That's fascinating. It seems like we've only scratched the surface of what sigmoid attention is capable of.
I think you're right. There's still so much to explore and understand, and that's exactly what we'll delve into in the final part of our deep dive.
Okay, I'm hooked. Let's unravel the remaining mysteries of sigmoid attention. All right, so we've seen sigmoid attention in action. It's computationally efficient. It holds its own against softmax in various tasks. But we also know there are some nuances, right? Things like normalization and bias initialization that are crucial for stability. Let's unpack those a bit further.
Definitely, you're right. Those elements are key. The papers go into quite a bit of detail about the specific strategies they used and how they impact sigmoid attention's performance.
It's like fine-tuning a high-performance engine, right? You need just the right settings to get the most out of it.
Exactly. They found that careful tuning of normalization techniques was essential for preventing those large initial attention norms from causing trouble during training.
Right, because if those norms get out of control, the model can become unstable and learning becomes a mess.
Precisely. And then there's bias initialization, which is all about setting the starting point for those relevant scores.
Because remember, Sigmoid can produce some pretty large outputs early on in training, right?
Exactly, especially when you're dealing with longer sequences. So they had to find ways to counteract that potential for explosive growth.
So what do they do? How do they tame those sigmoid outputs?
Well, they experimented with different bias initialization strategies, and they found that using a bias term of negative log n, where n is the sequence length, significantly improved stability.
Negative log n. Okay, that sounds a bit technical.
It is, but the basic idea is that the longer the sequence, the more negative the initial bias, which helps to offset those large sigmoid outputs early on.
So it's like applying the brakes a bit at the beginning to prevent the model from veering off course.
Yeah, you could think of it that way. It's all about finding the right balance between unleashing the power of sigmoid attention and keeping it under control.
Makes sense. But even with all these optimizations, I'm guessing there were still some challenges, right? No system is perfect.
You're right, there's always room for improvement. One thing they observed, particularly in large language modeling at very long sequence lengths, was the occasional occurrence of gradient norm spikes.
Gradient norm spikes. Now, those sound a bit ominous. Remind me what those are again?
So you can think of gradient norms as representing the size of the steps the model takes during learning. When those norms spike, it's like the model suddenly taking a giant leap instead of a small step.
Ah, okay. And those giant leaps can cause problems, right?
Exactly. They can lead to instability, unpredictable behavior, and basically throw the whole learning process off track.
So even with all the stabilization techniques in place, sigmoid attention can still have moments of unruly behavior, especially when dealing with those massive amounts of text.
It seems that way. They noticed these spikes were more prevalent at extreme sequence lengths, like 4096 tokens or more.
So pushing the limits of what these models can handle.
Exactly, which suggests that further refinements to those stabilization techniques might be necessary, specifically tailored for those longer sequences.
So there's still work to be done, especially at the cutting edge of large language modeling.
Definitely, but even with those challenges, the overall takeaway is that sigmoid attention has emerged as a serious contender in the world of transformers. It's not just a theoretical curiosity, it's a viable alternative to softmax with some unique advantages.
Like we've uncovered this hidden gem with the potential to really shake things up.
And that's what's so exciting about this research. It's opening up new possibilities, challenging existing assumptions, and paving the way. Oh, hey, welcome. What's up?
Hey, thank you for having me. Can we explain the regularity properties of the sigmoid attention?
Well, hello there, and thanks for chiming in.
Absolutely, we're happy to hear from you. It sounds like you're interested in the theoretical underpinnings of sigmoid attention.
Yeah, you're right on the money. Convexity and regularity are key concepts. Let's unpack those a bit.
Right. When we talk about a convex plan in the context of machine learning, it's basically about finding a nice, smooth landscape for the model to learn in.
It's like trying to find the lowest point in a bowl versus a Rocky Mountain range. The bowl is the convex space.
Exactly. With a convex loss function, you are guaranteed to find an optimal point.
But sometimes the loss function isn't convex. This can lead to the model getting stuck.
And that's where regularity comes in, helping us understand how smooth the landscape is.
Right, we talked about this concept earlier with the Lipschitz constant.
That's a measure of the function's smoothness. It tells you how much the output of the function can change in response to a change in the input.
So a lower Lipschitz constant means a more regular and stable model.
And that is precisely one of the theoretical advantages of sigmoid attention. We found that its Lipschitz constant is lower than that of softmax attention.
Yeah, that was a pretty big deal. It suggests that Sigmoid attention is more robust and easier to optimize.
Right, because the local Lipschitz constant of sigmoid attention grows like R pats, whereas softmax attentions can grow like R is R. So,
Sigmoid is not just fast, it's also more stable, in theory at least. We did cover all that earlier, so I hope that clears things up.
yeah, and we can always loop back to any of this if you have more questions. But in the meantime, let's get to the final takeaways.
You got it. So where were we?
We were saying that this research is challenging existing notions and opening new possibilities, right?
Exactly. And on that note, let's wrap things up and bring it all together.
Right. So, to summarize, we've gone through the ins and outs of sigmoid attention.
Yeah, we started by looking at the core differences between Sigmoid and softmax,
Then we dove into the theoretical properties of sigmoid attention, including that it is still a universal function approximator.
and that its improved regularity could lead to better training stability.
We also discussed those important techniques like alibi, layer scale, and hybrid norm that help stabilize sigmoid.
And the FLASHSIGMOID implementation that makes it competitive on speed and memory.
That's right, and we saw that it's performing really well in language, vision, and speech tasks.
So overall, it's clear that Sigmoid is a powerful alternative to softmax.
Absolutely, it's a compelling option and definitely something to keep an eye on as it continues to develop.
Well, that's all the time we have for today. Thank you for joining us and for your insightful questions.
Yes, thank you. It was great having you with us. We hope this deep dive was helpful.
And we hope to see you again next time.